Hello all, it's me again. I'm here to talk to you about the last lab, the lab on magnetic dipoles. It's a fairly straightforward and easy lab. There's two aspects to the lab, and I'm going to talk about just the first one this week, and then I'll do the second part next week. You already have the lab, so you could read about it all. So the question this week is simply to collect data to show that the force law between dipoles is an inverse fourth power law. So like Coulomb's law or the universal gravitational law is an inverse square law. So it falls as the distance gets bigger, it falls as 1 over r squared. Well, the force between dipoles falls as 1 over the fourth power of the distance between the dipoles. Let's talk about dipoles for a minute and review our electricity magnetism. Let's talk for a minute about electric dipoles. When I say electric dipole, you probably think of a little plus and minus charge, two charges, equal charges but opposite, plus and minus charges, separated by a little distance d. And has the dipole moment, the measure of that is a dipole moment p, which is the charge of one of the charges times the separation distance, qd. It has units, coulometers, for example, as the dipole moment. So if you think about it, if you make d really, really small, you put if those two charges were right on top of each other, they'd cancel each other out, and you'd have zero charge and you would have no field. So the dipole is the dipole source is the thing that gives you a field, not so much by virtue of its charge, but by virtue of the separation between the charges. Now a real dipole, you can have a point dipole conceptually. A real dipole is sort of the limit that as the distance of those two charges gets smaller, the charges go up so that the product of the charge times the distance stays constant. So the point I really want to make is that you really don't have any charge, you just have a little bit of separation, and so the field that you get is weaker. Famously, the dipole electric field falls as 1 over r cubed, and today's lab is about the force between dipoles, which we're going to show falls as 1 over r to the fourth. I've been talking about electric dipoles. The same thing is true for a magnetic dipole. What's important about a magnetic dipole is that's the simplest source. In electrostatics, you have monopole sources, charges, but in magnetostatics and magnetodynamics, you don't have any monopole sources. The simplest source is the dipole source. We're going to use essentially manufactured magnets. Here is a stack of them. They're very powerful, actually. They're very small, and they're very powerful. It's hard to pull them apart, and they want to stick together. And we're going to use 2 of these, and we're just going to measure the force between them when they're in attractive mode, so they're in this orientation where they pull on each other, and then we're going to measure the force on them if I turn this guy around. When they repel each other and I can't push them together, we're going to measure that force as a function of distance, separation distance. Okay, so here we go over to the table. I'll show you how that goes. So standing back from the table, there's a couple of parts to this. I'll show them to you from afar, and then I'll come in and show you the individual pieces. Back here, I have a ring stand, and it's just simply a holder. And on that ring stand, on the bottom of the ring stand, I can't even get down there, right at the bottom here, I need to focus. That's a little better. You can see one of those little magnets. Okay, so that's there, and that's in a fixed position aimed down. And then over here, let me focus in a little better. I have the second magnet. It's a little hard to see this, but this device here is a little scale, and it's sitting on a lab jack. So it's a scale on a lab jack. And the scale has a readout up here that tells me how many grams or ounces or whatever unit I want to choose is on there. The idea, if I can figure out how to show you this, is to I'm going to turn this guy around, is to align them so the bar magnet rests directly above the magnet on the scale. And then, of course, the scale will read the force between them, basically. So the idea is to pull the magnet away, tare, T-A-R-E, in other words, calibrate the scale so it reads 0 like this, and then bring this over and measure what the scale says now, and that's the force between the magnets. Now I want to vary the separation distance. Let me zoom out a little bit. I'm zoomed in too far. I want to vary the separation distance, so the idea here is that I can adjust the crank here on the lab jack to move the bottom magnet up and down, closer or farther away. By the way, I can also check alignment because I can move this lab jack side to side until the reading on the scale is maximum. So then I know they're really lined up. Finally, I need to measure the distance between them, and there's some language. So I have a ruler here. There you go. There's a ruler that's clamped here, and what I did was I measured at the beginning. I put them very close together. Let me duplicate that for you. I turned the lab jack up so they were as close together as I was going to get them. I carefully measured the distance between from the top of one magnet to the top of the other magnet, which is the same as the distance from the middle of one magnet to the middle of the other magnet. In that same configuration, over here, I aligned this ruler with the tabletop, and I measured the reading. I call that S0. And then after that, I cranked this thing down to get different distances, greater and greater distances. I went roughly a millimeter a section, and by monitoring the change in the reading over here, I could figure out what the change in the distance is here. And the data table that I'm going to send you has that information on it. Then I took the magnet off this thing. Here it is. Here's the magnet. Whoops, where is it? Here's the magnet. And I turned it over, and I put it back on, and I did the experiment again. And now it's the attractive one, and so now the scale is being pulled up, and it reads negative values. And so I generated data that way. I think everything else on the data sheet is self-explanatory. I can show you the top sheet. I actually, let me focus this pretty good here. So I have a sketch. Label shows you how to figure out what the distance is. And a couple of notes I took, like if it was my lab notebook. And then I took some data here, and it continues on other pages. Okay, I think that's it for me. Signing off. Bye-bye. Stay healthy, stay well.